Hello everyone, welcome to week 7 of Incomplete Data Analysis. In this week we will keep studying the EM algorithm and we will start by applying it to a problem where in fact the EM shines, to mixture models. So let us start. We will consider a very popular dataset that is available on R, and the dataset is the Old Faithful dataset, and it consists of 272 waiting times between eruptions for the Old Faithful geyser in Yellowstone National Park in the US. And here on the left we have an image from the internet from an eruption from the Old Faithful geyser, and in the right here we have the histogram of the waiting times between eruptions and the dataset that we will be analyzing. And as we can see, if we think about a sampling distribution to fit to this data, for instance, if we think about the normal distribution, it's clearly inappropriate, right? Because we see that we have kind of two modes, so a single distribution that fits something like this would be inappropriate. But for instance, if we consider a mixture of two normal distributions, maybe we are doing something that it's reasonable. So let's try to fit to this dataset a two-component mixture of normal distributions. And how does it look like? So we are posed for our density function the following model. It's the one that we have here. So we have two normal components and we are in the most general case, so the means are different and they have to be right. If we look here, we see that if we think of one of the distributions to be this one, if we think about the mean somewhere around here and also somewhere around here, for the two normal components, their means need to be different. And the standard deviation or the variance of the distributions, it's here, it's not very clear whether they are too different or not, but let us put ourselves in the safe side and assume that by default the two variances are different. Then if the data tell us that the estimates are very similar, there's nothing wrong with that. Well, we are estimating a further parameter, but apart from that, there is nothing wrong with that. And we know that our the model that we are positing for F, it's nothing more than a mixture of distributions, a two-component mixture. We have the first component here, the second component here, and then we have the weight that we give to the first component, that it's P. And we know that if the first component receives weight P, then the second component will receive weight 1 minus P. And so what are the parameters here in this context? P, the weight of the first component, the mean and the variance of the first component, and the mean and the variance of the second component. So we have 5 parameters here. And if we want to write the likelihood function, it's just we have the density function here. So we know that the likelihood is just the joint density regarded as a function of the parameters, right? So we have nothing more than this expression here. And if we want to find the maximum likelihood estimates of the parameters, then in the usual way, what we do is, okay, now I have my likelihood, I will write down the log likelihood. And that's what we have here in the bottom. But something that we can immediately notice is that my log likelihood, I have the sum of the log, and inside the log, I have the sum of two distributions, right? I have the first and the second component, and the log of the sum, it's not the sum of the logs, and so my maximization is not trivial. And that's where the EM algorithm comes in. And the idea is, okay, my main problem is that my likelihood, and by consequence my log likelihood, is not very analytically tractable if I want to maximize or to do the calculations analytically. But if I knew the group that each observation belongs to, then I could simply fit a normal distribution to each group, and I could simplify my likelihood. And so, okay, let's bring an additional or a further variable to our problem. And so let's define Z, which is an unobserved or a latent variable or group indicator, in the sense that we do not observe Z, and Z takes the value by construction. We are saying that Zi will be 1 if Yi belongs to the first component, so the component associated to short waiting times between eruptions, and it will take the value 0 if Yi belongs to the second component, or the component associated with long or longer waiting times. And we will have as many Z variables as observations. So if I have n y's, I will have n Z observations, right? Because Zi is associated to yi. And so we now can see some of the components that we need for our EM algorithm, right? I can think that my observed data are my y's, my waiting time. So that's what I have here. My observed data are my y's from 1 up to n, and then we know that for the EM algorithm to work, we also need some missing data. In this problem, we don't have missing data in our original data, but if we can frame our problem as a missing data problem, we will see that this simplifies. And my Z's, they are, as I have said, latent or unobserved, and I know that they will form my missing data, and that's what I have here. Okay, and we also know that because we are saying that Zi is 1 if Yi comes from the first component, and the weight that we are given to the first component is P, and P lies between 0 and 1. And we also know that then the probability that Z of I is equal to 1 is exactly P. Okay, and now the good thing is that my complete data likelihood, so my complete data is formed by the y's and the z's. My observed data are the y's, my missing data are the z's, and the complete data, which is formed by the observed and missing data, is formed by the y's and the z's. And now it can take this expression. Why? Because if Zi is equal to 1, this component will be active, correct? And I know that by definition, Zi is equal to 1 when yi comes from the first component. When Z of I is 0, I know that this component will not be active, but this one will be active. And I know that Zi is 0 when yi comes from the second component. And the good thing is that by using the latent variables, the Z's, they are latent because I do not observe them in my data set. I do not know whether an observation is coming from the first or the second group. I can write my likelihood as the product of the two distributions. I don't have the sum, and this will simplify my log likelihood and my calculations. Okay, so now if I write the log likelihood of the complete data, I know that this will be And that's the log likelihood of the complete data. And now we are under the framework of the EM algorithm, right? I do not observe the Zs, and I will proceed to the E step, right? And in the E step, what I need to do is to come up with my Q function, which is the conditional expectation of my complete data log likelihood, and I'm computing the expectation with respect to what is missing. In this case are the Zs, given the observed data, the Ys, and the current parameter estimates, say theta at iteration t. So what I want is this expectation. And now I will plug in my complete data log likelihood. And here I can just replace what is observed. There is nothing wrong, right? But I know that what is observed is the Ys, right? Given the Ys and theta at iteration t. And now I know that everything that does not depend, we are taking the expectation with respect to Z, and everything that does not depend on Z is to be regarded as a constant. So in particular, what is inside here is regarded as a constant, and here as well. So I will just take the expectation of Z. Okay, so I know that and now to complete my E step, my expectation step, all I need to do is to compute the expectation of Z of I for I from 1 up to n, given Y, what I observe, and theta at iteration t. So I know that first, conditioning on all of the y's for zi is irrelevant. The only value that I need to condition is on yi, right? Because zi will be 1 if yi comes from the first component and 0 if yi comes from the second component. So I don't need information if I'm talking about z1, say about y2, y3 up to yn. For z1, the only quantity that is informative in my data is y1. And so I can write like this. It's just a detail, but I think it's important to think about it. And zi is a binary random variable taking the value 0 or 1. And then I know that this is the probability that zi will equal to 1 given 1 times this, right? Plus 0 times and this is the probability of z of I being equal to 1 given yi and theta t. And now I can use Bayes' theorem, and in particular I know that I can write this as f of yi given that zi is equal to 1 and theta t times probability that z of I is equal to 1 given theta t and f of yi given theta t. Okay, and I know that I will rewrite this again here. I know that I have the first one, the density of what evaluated at yi given that zi is equal to 1, I, because zi is equal to 1 when yi comes from the first component, right? So I have and this is conditional on sorry theta t, right? So I know that it's and then I know that this probability is I know that the probability of zi being equal to 1 is equal to p. Now if I'm conditioning on theta t, I know that this is p of t, so I will put it here. And I know that my density, it's my mixture model, right? So it will be I will need to and that's it. That's my expectation. And now I just need to plug this expression here in my Q function. And because this is kind of a long one, I will say that I will have one of these for each I, okay? And now I can finally write my Q function as and this is a value, right? Once I have what are the estimates at iteration t, this will be a value, be it what it is, okay? And now I will replace, I know that this is the log of normal density function, correct? So this is log of, say, correct? Plus, I will, sorry, but I will start it from here, plus, this is just replacing the density of the normal by its expression. Okay, and I can simplify further because I know that this is and the same for the second component. And that's it. Now I can proceed to the M step. And in the M step, I will take the derivative of my Q function with respect to my parameters that in this case, as I have mentioned, are P mu1, sigma 1 squared, mu2, sigma 2 squared. Okay, I will do for P mu1 and sigma 1 squared, the calculations, the remaining ones are similar, okay? So now let's take the derivative, the partial derivative of our function Q. So I know that if I look, this is with respect to P, 1P correct, minus, and that's it for the derivative with respect to P. Now let us set it to 0 and solve for P at iteration t plus 1. And now I have that these two terms, they cancel, and I have that and I already have the M step or my updating equation for P, the weight of the first component of my mixer model, and it is given by this equation. Now I will derive the updating equations for mu1 and sigma 1 squared. And I know that what I have is sorry, it's if we come here, it's here, it's this bit, so I still have the minus 1 over 2 sigma 1 squared. So I can write it as and it is. And now setting it to 0. And that's my updating equation for the mean of the first normal component. And at last, let's derive the updating equation for the variance of the first normal component. If we go back, so have this term, and I have this one. And then I have -1. Let me just look at it. Plus sorry, it's to the power of 4. Oh, power of 4. Okay, of that's it, correct? Now, when I set the partial derivative equal to 0, and this implies that at iteration t plus 1, I have, and now if I'm updating the parameters sequentially, so if I started with p and then mu1, I don't have to follow this order, but it's kind of a natural one. Now when I write mu1, I have the most updated value, right? Because I've already, then when I implement in R or any other software, I have already the most updated value for mu1 at iteration t plus 1. Okay. And that's it. And for you can easily see that the estimate at iteration t plus 1 for mu2 is and for the variance of the second component it is Let me just check. I think they are correct. Yes, that's it. Sorry, here the square is missing. It was come from here. Okay, so okay, that's it now. Once we have our M step completed, so we have updated estimates of the means, the variances, and the weight of the components. So I go back to the E step, I replace my most updated values, then I proceed again to the M step, and I iterate until some convergence criterion has been met. Okay, and I have here some slides in blank. And after implementing this procedure in R for fitting two-component Gaussian mixture model, we have the code available here on Learn as well. That's what I have obtained, and I think it looks pretty reasonable, right? I can my fitted model, or my estimated density, more properly speaking, is the line in blue, and I can see that it nicely follows the histogram. So for this problem, a two-component mixture model worked very well. And in general, we are not restricted to a two-component mixture model. I have more generally, or I can have, sorry, more generally, k components, and I don't need to have mixtures of normals. I can have mixtures of other densities, and that's exactly what I have here. The only constraint is that the weights associated to each component, they need to add up to 1, and I have here the case for a k component mixture model. That's what I have here. It's very similar to what we have been doing, but we have more means and more variances rather than just two. We have k of them, and the weights associated to each component. In fact, we have k of them, but because they need to add up to 1, in practice, I only need to estimate k minus 1 of them. And mixture of normals are important because it can be shown, or it has been shown in the literature, that provided that we use an appropriate number of components, mixture of normal models, they can approximate any density on the real line. So any density that we can think about, mixture models that we can think about, and that's defined on the real line, mixture models, mixture of normals, provided that we use an enough number of components, will approximate the density well. Then how we choose an appropriate number of components here, because it's a very popular example, we knew that a two-component mixture model was all that we needed. In other cases, it might not be as clear the number of components that we need, but that's a completely different topic, and I will not enter into the details. Here, the goal is just to illustrate how to apply the EM algorithm to mixture models. And before we conclude this part, I should warn you, I will not enter in all of the details, but I want to pass this message. Mixture models, they suffer from the well-known label switching problem, also known as label ambiguity. And this refers to the fact that there is nothing in our likelihood that is able to distinguish mixture component k from mixture component k prime. And this means that if I if I do the permutation of the thinking about k component mixture model, if I permute the k labels, this will result, sorry, in the same model for the data. And this is kind of abstract, but I have an example here. So think that we have a two-component mixture model, and that our weight associated to the first component, P1, is 0.3, and then I know that because they need to add up to 1, but but I want to have P1 and P2, although I only need one of them because they need to add up to 1. But just to make my point, then P2 needs to be zero point 0.7, and then the mean of the first component is 1, and the mean of the second component is zero point 0.5, and the variances of both components are equal to 1. And let's call this scenario A. And then if I change, now I know that, now I say that P1 is zero point 0.7, P2 is zero point 0.3, so they just switched values. Mu1 is 1.5 and mu2 is 1, so I have switched the means as well, and the variances, they were 1, and they obviously are 1 as well here. So this is scenario B. And so the density associated to scenario 1 is this, right? I have P1 here, it's mu1 sigma 1 squared, mu2 sigma 2 squared, and that's my density. And then if I, for scenario A, and then if I use the parameters that I have permuted from scenario B, this is my density, right? This is my P1, this is now my mu1, and this is now my mu2. And as you can appreciate, these two, let me just use a different color. The one in blue is exactly equal to the one in yellow. Okay, so if we are just interested in estimating the density, then it's fine. If we want to make inferences or to say something about the mean of the components, so we need some more care. Of course, for our data, because the modes were, the two modes of the data were well separated, we have no problem in identifying what is mu1 and mu2, but sometimes this might not be as clear as in our case, and so if we are interested in estimating the density, again, no problem. Making statements about the means or the variance of the components, we need some more care. Okay, and usually, and in our case, the modes, as I said, are well separated, and in our code, as long as the initial values for the mean of the first component is smaller than the initial value of the mean of the second component, so we do well. If we do not do this, we might obtain that, just to make it a little bit more concrete. Here we know that the mu1 is about 55, right? And that mu2 is about 80, correct? Just by looking at the histogram. And if we set up an initial value for the mean of the first component greater than the initial value of the mean of the second component, kind of does not make sense if we look at the data, but still then our mu's will be reversed. Again, I obtain exactly the same density, just that the means are have switched. I do not want to enter in many details because this is a kind of open problem in the literature. There are still people working on how to fix this, but I wanted to warn you about this problem in mixture models. And finally, just to make the point that when we have different modes in our data, mixture models are an obvious choice, but in fact mixture models, they can be used even when we have like skewed data, as this example here. I can also handle this with mixture models. Here it's skewed to the right, skewed to the left. So, and as I've said, this is no surprise because I've said that, for instance, mixtures of normals, they can approximate any density on the real line. We just need to make sure that we use an enough number of components. And last slide, I've uploaded to learn a paper that I think it's a very interesting one, and the title is Numerical Maximization of the Likelihood, a Neglected Alternative to the EM Algorithm. And basically the paper advocates the use of direct maximization of the likelihood through numerical procedures in several well-known problems where the EM algorithm is the gold standard solution. Uh, I think some of the examples are really interesting. For instance, for this data, the old faithful data set, I've tried maximizing directly the log likelihood without recurring to the EM algorithm, and it was very unstable. And on here we only have two components. I can see the potential for trouble if we have more components. Here, with only two components, we already had, or I had trouble uh, using Optim to maximize my log likelihood without using the EM algorithm. Nonetheless, I think it's an interesting, and it's not too technical, so I think you can follow it quite well, and it touches an example that we will be doing in workshop for a mixture of Poisson distributions. And that's everything for this part. I see you in the next video.